So now we start the free body diagrams and equilibrium analysis of what's called frames and machines. So the previous section had to do with trusses, so it's more for civil engineers. Now for this section, we look at frames and machines, and it's more for mechanical engineers. So the concept is the same in terms of being aware of what's considered to be external forces. And if we section materials or if we unpin them from their supports, we will now expose internal forces, which converts them over to external forces on free body diagrams. So what I'm going to do now is just show you folks how to do these free body diagrams of frames and machines. So suppose I have a structure that's pin connected here. It's also pin connected there, and here we have another bar that's pin connected here. So we'll call this points A, C, and we'll also call this point B. We'll call it B. And there's a little ledge right here that's attached to member BC, and it's fixed to it. So suppose I apply a moment, and I also apply a load P, and we'd like to determine the free body diagram of member AB and member BC. So in order to do that, we remove the pins, remove it from its supports. So we'll get member AB right here, and we'll get member BC right there. So now we draw the external forces and also the internal forces at supports A and C, since we released those members from those supports. So at A, the pin assembly prevented member AB from translating in the X and Y directions. Therefore, I'll have a reaction force in the X, reaction force in the Y. Same thing at C. The pin assembly prevented member BC from translating in the X and also translating in the Y. At B, there's a pin there, and that pin prevents member AB from translating in the X and Y. Therefore, we'll have reaction forces BX and BY. And those are just my assumptions, that I'm assuming that it goes to the left and it goes downwards. This point B is the same as this point B. Because we separated them, these used to be the internal forces, but since we separated them, they're now external forces. On member BC, I would also have to draw this force vector BX, but it would be equal and opposite in direction. And same thing here, it would be equal and opposite to what I assumed here. And I can't forget this applied moment. So that's my free body diagram. Let's do another free body diagram where we have a pin assembly and we have a bar, and on that bar I have a pulley, and it's attached to another equipment that we don't know where it's at, but there's a cable and there's tension in that cable, and the problem statement says this is at an angle of theta. So I will have this tension T, I will have this tension T, and it also gives us this angle, let's call this alpha. And at the very end, there's a weight that's attached to it. So there's two free body diagrams that we can draw for this particular frame. So I can draw the free body diagram of this rod, A, B, and let's call this C. So here is A, B, and C. So at A, the pin assembly prevents the frame from translating in the X and Y directions. Therefore, I'll have reaction forces in those directions. At B, I have the effects of that weight here, so I'll just represent it by W. And at C, I have the pulley, but I took that off. So at the pulley center is a pin, and that pin prevents this frame from translating in the X and in the Y direction. So I'll just assume it to be going in that direction for the X component and going in that direction for the Y component. The other free body diagram that I can draw is of the pulley. So here's my pulley, and this is point C. Therefore, I've already made the assumption that at pin C, my reaction CX is in the negative direction, and for the Y, it's going upwards. So I would have to do an equal and opposite force on the pulley. So it'd be CX, and since that's going up, I have to make it go down, CY. So those are the two free body diagrams for this frame.